So, okay, thanks for the introduction. I'm really happy to be here. I just think you have a beautiful campus. It was just really pleasant walking around. You have beautiful weather today, which is great also. I don't know if it's like this all year, but at least for today, it's wonderful. So it's definitely a pleasure to be here. Okay, so what I'm going to be talking about, if I can remember how to use that, is just some different versions of the fault prediction techniques. So Elaine told you the basic idea and what the basic model that we use to do the fault prediction. And essentially the reason that we use those 5 characteristics that she mentioned is that those were the easiest ones to get. So they came directly out of the MR database and were not difficult to collect, although, there was some work involved, but it was mainly one of getting the data to be clean, which is another whole issue. If anybody's working with big data, you know that there are lots of potential problems that can come up. But those characteristics were the easiest ones to get. We could get them right out of the database. So what I'm going to I'll just quickly review again what we call the standard model, which is those 5 characteristics, and then 3 variations of it that we investigated to see how they might improve the fault prediction results that we were able to get. And then at the end, I'll talk a little bit about some thoughts we had about trying to see if we could capture let's say, the propensity of individual developers to introduce bugs. And there are lots of issues with that which make it difficult. Okay, this is just to remind you now the way that we actually evaluate the quality of prediction. As she showed you with the tool, the model ranks the files in order of predicted most number of faults, and then that information goes to the developers or the testers. What we call the yield, it's the percent of the real faults that showed up in the top X percent, and as she said, you can pick any X that you like. The 20% seemed to be a useful number. We also looked at, we tried to generalize this thought a little bit, and we came up with something that we called fault percentile average, which is a way to eliminate using one specific percentage value, and we just averaged the yield over all the values of X. And in some sense, that's a more theoretically satisfactory way to measure it, but it's something that's actually hard for the developers to understand what we're even talking about there. And actually, all they really care about is to just see this ranking of the files. So if anybody wants more information about that, I can tell you about it, but it's just another number that we use sometimes. Okay, standard model. This pretty much repeats the slide that Elaine had. The negative binomial is the mathematics behind it. The output variable, the dependent variable, is the percent of faults, the predicted percent of faults, and then we have these 5 predictor values. And these 5 independent variables, predictor variables, these are all really directly accessible from the database, from the project database. So the easiest things to get. When we first were talking about this work, the first couple of years, we only had looked at these values, at these predictor variables. And a natural question that seemed to come up every time a talk was given was, as Elaine said, how come you didn't look at the influence of developers in some way? And one thing that people think about is the more people, there's a folk belief or an intuitive belief people have, the more people who work on a project, the more likely you are to have problems. Because, if you have 5 different people, then they don't all understand the same thing. They don't have the same concept of what's going on. If one person writes half the code and another person writes the other half the code, maybe there are just conflicts between those 2 things. So it would be natural to think that would affect the number of bugs. So that's the first natural question that came up. So the developer attributes that we looked at included how many people worked on the code. We also looked at calling structure. So what Elaine said is if if a file that has faults calls some other file, then does that mean that the other file is likely to have faults? But we also just looked at even simpler thing, just what's the potential interaction, never mind whether faults are in a file that gets called or does the calling, simply the more that a particular file interacts with other files. So the cohesiveness or the lack of cohesiveness of the software might be an influence on the number of faults that you would see. And then finally, we looked at not just counting the number of changes that were made to a file, but the extent of those changes, how complex those changes were. So that's what we call the fine-grained change metrics. Okay, so developer counts. We looked at 3 different ways of characterizing this. What we're trying to do always, just to keep in mind, we want to predict how many faults are going to be in the current release, in files of the current release that's being worked on. The information that we have available is all the information from previous releases. So the only thing that we look at in the current release is how big is a file in that release. Everything else comes from the previous release. So we look at how many different people worked on a file in the previous release, how many different people worked on a file in all the previous releases, the whole life history going backwards. And another thing that potentially might be interesting is if you have a file that's been in the system for a while, and then you have somebody who has never looked at it before, who's a new programmer for that file. Maybe that person is more likely to make mistakes than somebody who's experienced with it over a lot of previous releases. So these are the 3 things that seem naturally to be potentially useful for us. This information is also available in the database of the system, but it's not as easy to extract because you have to look at the history, and you have to make the database has to tell you who the people are who worked on the files. And this is there, but it's not as easily accessible as just counting the lines of code of a file. So, but it is also extractable from the fault database. Okay, this one is now for one of the systems that we looked at, and actually you're going to see that, I don't know if you remember the acronyms that named the systems on the slide Elaine had of the 9 systems. We kept changing the acronyms of the systems, so we sometimes call them by different things, so don't worry too much about it. This is one of the systems that, in this slide at least, is called BTS. So what this is showing, where's the pointer? Yeah. Okay, so this is showing the number of developers who work on a file versus the number of faults in a file, and for each of the 3 different ways of counting. So, okay, developers in the previous release. So that's just the black dots here. So if there were, for example, 11 developers that worked on a file in the previous release, for all those files, all files that had that property, the average number of faults was 4. The only one of these that really is frankly useful, for me at least, that tells something, is this one. So if we looked at the total number of developers that worked on a file in all previous releases, as that number gets bigger, there's some kind of increase in the number of faults, the average number of faults per file. Up to about this point, it's meaningful. Beyond this, it's really not meaningful because there are hardly any files that have so many people working on them. So this point, for example, which shows a very high number of faults, if you have 45 developers, or 44 developers, it may only represent one single file out of the hundreds that we looked at. So it's not really very meaningful here. And probably this point is also not particularly meaningful because just 11 people working on it in one previous release, very unusual. Maybe just 1 file or 2 files that had it. So don't pay too much attention to this one. Also this one, I think, don't pay too much attention. So as I said, this one is probably the most useful thing. And in fact, what we're going to find out is that cumulative developers, all previous releases, it's the only factor that actually did make a noticeable change in the prediction quality. So I'm giving away the answer right now, but that was in fact the case. So, okay, we're going to again look for this system BTS, and I'm just going to show you the number of actual faults that were captured in the predicted 20% of files across the releases of that system. This system had This is the one that had 35 releases. And this chart just starts with release 6. I really don't know anymore why we dropped off the first 2 or 3 in here. But anyway, maybe the slide is just too big. Anyway, okay. Okay, so the standard model does pretty well, especially when we get to the later releases, which we're well above 80% all the time here. Okay, next one is going to take this slide, this graph, and just overlay it with the prediction value when we add to the model the number of developers in the previous release. So, okay, so this is if we have just the developers in the previous release added to the model, the prediction hardly changes, right? Almost exactly the same, so didn't give any particular advantage.
And sometimes it was worse.
Actually, in this case, you know, if you look, I think there's only one place where it's actually worse, right? This one it's worse, this one it's a tiny bit better. Oh, this one it's a tiny bit worse too, yeah. But essentially almost the same. Let's look at, if you look at new developers, okay? That's even closer, I think. Well, this one is a little better, this one's a little better. But, you know, this is not significant at all. What about now if we look at the cumulative developers? You probably expect now it's going to be great, but in fact, it's hardly different. And in fact, here, it's interestingly enough, in some cases it got, yeah, maybe 5 points worse. Some cases 5 points better. So this one also, for this system, for this BTS system, none of these actually had much of an effect in general, okay? So, all right, so why is it any good at all, actually? Well, for this one, we decided it doesn't really make any difference. Here's for one other system, which in this slide it's called provisioning 2. And here, I'm just showing the cumulative developers, and here it seems like a noticeable improvement. It's not very much, right? I mean, 3 or 4 points maybe improvement. But this was statistically significant, so we were able to grab this one and say, okay, if you look at cumulative developers, this can make a little bit of difference, a little bit of improvement over the original standard model. And we saw the same, I don't have any more charts of this, but we saw the same for a couple of the other systems that we looked at. So our conclusion when we look at these counts of developers is that this one with the cumulative developers, it's the only one that really ever gave some improvement. In some cases it gave no improvement. So we were, you know, willing to publish this and say this was a result that may actually be helpful. I'll even give away the entire point right now of the whole presentation I'm going to give. This is the only change to the model that made any significant improvement at all. So the calling structure and the fine-grained change metrics, but I'll talk about, but the result is going to be that none of those actually gave significant improvement. So actually that's a useful result, and a useful research result, because it says that at least for the systems that we looked at, those characteristics are not going to help you improve the prediction. And in fact, both the calling structure and the fine-grained change metrics are more difficult metrics, more difficult values to collect than the ones that we've looked at so far. So maybe it's not worth the time or the effort to collect those. Of course, we should always be looking at more systems and seeing if those same results carry through. But at least for the ones that we have looked at, for the 9 systems we have looked at, this is the only thing that really made a difference. Okay, this just what I just said before. So let's look at the calling structure now. So this is kind of a standard, simple-looking picture. We want to be looking at a file which has methods that are maybe being referenced or called from other files, and it also in itself in this file it's also calling some other files. So essentially we want to look at, first of all, just the complexity of the structure of the file itself. So how many files are calling it? How many files does it call? If that's more complex, does that make it more likely to have faults? One thing. Then we want to look at the likelihood that this guy is going to have faults if these guys have faults, or if these guys have faults. We also want to look at, given certain, if there's a higher number of changes that occurred here, or higher number of changes that occurred here in the previous release, does that make this one more likely to be faulty? So we looked at, in fact, all of these different ways of counting or of measuring the complexity of the calling structure, and tried to see if any of these variables increasing in value made the faultiness more likely of that file in the middle. When we did this, we did not have access so to do this, you don't look into the change database now. Now you have to look at the code, because you have to do a source code analysis, or static analysis on the code to look at the calling structure. We had very poor access to code analysis tools at that time, and we only did this for files that were, I guess, even C, C++, and Java. So, wait a minute. Okay, wait a minute. Let me see. Okay. So we just looked at, that's right, not even Java. We didn't even have Java. We didn't look at Java here at all, yeah. So we just looked at this subset of all the files in the BTS system. So there were some other file types. We didn't look at those. I think that these files were something like 85 to 90% of all the files in these systems. So the way we did this was, it was a greedy procedure, essentially. We built the model starting with identifying the single variable, the single independent variable that had the most effect on predicting the faulty files. And then we successively added variables one after the other that increased the fault prediction quality. And so the first model built from the single best attribute to the single best independent variable. Each succeeding model, we added the single attribute that improved the prediction the most. And then we stop doing this when we get no more improvement. So that's how we did this particular analysis. And let's see, just to go back to here. So we considered three sets of attributes. So first we started without using the calling structure. So this was the same information that we used in the standard model, but we built the models using this greedy procedure, just so we'd have this as a basis for comparison. Then we looked at everything, all the code attributes and the history attributes. History attributes means the prior changes and prior faults, and including the calling structure information. And then we thought, well, let's see, maybe the calling structure gives enough information that we can get prediction results that are just as good as what we got without using the history, without using the prior faults and the prior code. So just another thing that we were looking at. Okay, so this one now is without using the calling structure when we did the greedy procedure. So the best single attribute was simply looking at the number of changes in the previous release. And here we got nearly 70% of the faults already, just by using this one. Then we add to the model the size, then whether or not a file is new in the release, and then at this point we had decided that the cumulative developers is a useful attribute, so that's included in the models we were using at this point. We add cumulative developers, new file in the previous release. New file here means new file in the current release, new file in the previous release, and then finally just the faults in the previous release. It's interesting that this one came so far to the end in terms of improving. So we got up to this 77% for that system. Remember again, just looking at the C++ and the CSQS files. Okay, so this is somehow our base standard model plus the cumulative developers. Okay, next we look at all of these things, and this is pretty interesting actually, because when we add the calling structure attributes as something, it turns out to be, not only is it not helping any, it's actually hurting a little bit. So again, the first most useful single attribute is changes in the previous release. size of the file, new file, and finally here, if you count the number of files that are called from the one that you are trying to predict in the previous release that have faults, then that adds, well, it adds about 3 points in terms of the prediction. But then we stay the same here, and actually we just should have just stopped here. I don't know, we looked at one more to see, and the best one that we added actually decreases the value. So you might think it's strange, how could you decrease if you've already gotten to a point, get worse? But the point is that it's a regression model. So you have a regression model with one additional variable, and the fact that you get a lower result, it may be a little surprising, but it's not contradicting anything. Okay, so basically what this is telling is that the calling structure doesn't really help at all. We also looked at leaving out the prior faults and prior changes variables, and we don't, this is the best that we got, and I think the next one must have gone. I don't think it's just because it didn't fit on the slide, because we could compress the picture. But we didn't get any better than 75% here. Without using the prior faults or prior changes. Okay, so of course we looked in the previous release and we see we have the changed files that have been called without counting the number of changes. Okay, so much for calling structure, at least for this limited study that we did. We did this for one system. We did it for two. This is only showing it for one, and the results for the second one were actually, it was very poor. We didn't do the analysis completely through to the end of the second one. So basically, as far as this goes, calling structure is not helpful. Again, that's something that should be done for more systems to see if the same results carry through. Okay, so the calling structure generally, overall, does not help. The history attributes, either with or without, they do improve the results. It's for one system. We should do it for more systems.
The journal paper.
Okay. The journal paper has charts for two. Yeah, it's true. It's true. Okay, let's talk about measures of code change. In a way, this one's the most interesting. To me, it's the most interesting one, actually. How can you measure code change? You can do some very simple thing. You can just say, is a file changed or is it not changed? This is just a binary value. In our standard model, we went a little beyond the binary value. We counted the number of changes during the release. But obviously, there are more detailed things you can do. So we can look at how big is the change. So we can look at you can look at the lines added, the lines deleted, the number of lines that were modified. And we also looked at something that we called relative churn, or relative change. If you change 50 lines in a 50-line program, you're changing 100% of the program. If you change 50 lines in a 1,000-line program, you're changing 5% of the program. So it would seem, at least intuitively, you might think that changing the 5% of lines is less likely to introduce faults than changing 100% of the lines. It's not an unreasonable thing to expect. So we wanted to check and see if that, in fact, was the case. Okay, here we did this work on two systems. These are the last two, I think, in the chart of 9. Whoop, wrong button to push. Yeah, same thing that happened to you. Wow, amazing. This is a fancy device, right? Tricky device, unpredictable device. Okay, so just these are simple characteristics of these things. So the top one is 1.5 million lines. This one's 250,000 lines, and it's interesting that it's a much bigger system. So maybe that it has 400 faults per release versus 90. Maybe that's a reasonable expectation. Okay, so now we're going to try to measure. We want to see the influence of the changes on files. So this is just showing where the faults, distribution of files. Okay, this is just showing the distribution of the files. So in both cases, more than 80% of all the files, as you go from release to release, more than 80% aren't changed at all. The new ones are the blue ones, and the changed are the red ones. And okay, so just to get an idea of this. The next picture is going to show the same circles, but it's going to show the distribution of the faults with, I hope, the same colors. Okay, so here's where the faults are. So in the unchanged files, virtually no faults are found. Here you can actually see the sliver, and in this one, it's not 0, but it's pretty small. You cannot really see it on the picture, I think. Okay, and the the changed files is where all the faults occur, or where the vast majority of the faults occur. Okay, this is the same picture, but just in a graph like this for the IC system and for the AR system. Okay, so obviously the changed files is where the faults occur. This is where you could not see that sliver. There is actually a non-zero value there, but it's a pretty small value. Okay, so what I'm going to show you is how the results I'm going to show. First, we have univariate models. So it just means a prediction model based on a single one of these variables, which single variable is giving the best result. Then what we did is we took what we called a base model, which is a subset of the standard model, which does not include any of the changes of the change factors at all. And then we took the base model and we added to it each of these things and see if it makes a difference, if it improves the fault prediction in any really significant way, in any useful way. Okay, and now these are measured not in terms of the top 20%, but in terms of this fault prediction average that I mentioned in the beginning, which is the average over all the possible values of where the cutoff point is. So it's not just the 20%. Okay, so these are the univariate models. So the standard model is up here in blue for this system. This is for the system IC. So the standard model gives, how much is it? About 92% as the fault prediction average for the system IC with the standard model. If we use prediction model based on just a single variable, nobody does that well. The best one is just the size. Changes in the previous release is almost as good, and then, okay, they're getting worse like that. So again, but just single model. Actually, what this is saying is that if you really don't have a lot of expertise and you don't want to spend a lot of time building models, just count just look at the size of the file, and you get a pretty good prediction of where the faults are going to be. Okay, now we're looking at the base model and the added variables. So again, there's the standard model. And now, if we take the base model, which includes the size, the number of releases that the file has existed, so the age of the file, and the file type, and add to it just a count of the previous changes. So this is this is almost the standard model at this point. Okay, it doesn't include the count of the number of faults, and it doesn't include the number of changes in 2 releases previous. You get, I think this number is just slightly less than the standard model. If we added, if we counted individually the number of additional lines added, lines deleted, and lines modified, we actually get a result that's a little bit less, not quite as good. It looks like about, is it the same? Or just slightly less, right? Than just counting the total number of changes without regard to how big those changes were. And it just drops in that way. Down here, it's the base. So just using those 3 values, it's noticeably worse. It's worth realizing that in some sense this graph is, well, it's not tricky to interpret, but it can be misleading in a way, because look at the scale down here. It's going from 89 to 91, 92, 93. So there's very little difference from here to here, right? So is this really significant? It's probably not really very meaningful, okay? So maybe this is an example of how you can use statistics to confuse people, right? You see statistical charts in the newspaper that show great things about whatever, and maybe sometimes they're similar to this, right? So these differences are not terribly meaningful. Okay, that was for the IC system. Here's the AR system, the same thing, and it's very similar, right? I mean, the standard model gives this. In this case, interestingly enough, the base model plus the previous changes actually slightly outperforms. But again, the differences are so small that it's not telling something that's really particularly helpful. Okay, so to summarize this, let me go back for a moment. The churn models, or the fine grain change models, which is anything that has adds, deletes, modifications, I mean, they do quite well. Okay, so if you only have these things plus the base model, you're okay. You're doing a pretty good job of predicting. But on the other hand, why use them if the simpler ones do just as well? Okay, so it's certainly true. Churn can be an effective means for improving over models that don't include it. But, okay, this improves the accuracy if you don't have any other change information. But you don't need it, right? You can do just as well without using it. Just counting the prior changes, you get just as well, or even better. Prior changed, am I going to get into trouble now? Yeah. Prior changed just means not even counting the number of changes, just counting, is it changed or is it not changed? So just the binary yes, no, was it changed, is nearly as good if you add that to a model without any other change information. Okay, of the three, lines added, lines deleted, lines changed, the lines added seemed to be, at least for the systems we looked at, was the most effective one. Okay, that might be different for other systems, I don't know. Again, something that could be looked at for other systems. Lines deleted was the least effective single one. And the relative churn, which I personally would have thought would give you some really meaningful differences, didn't seem to be any different from the total churn. I'd like to look at that again for some more systems, just to see if that's always the case. Okay, so this is overall summary then of these three different types of ways of modifying the standard model. And basically, standard model performs very well. The augmented models add very little. In the case, the only one that really seemed to be strongly better was, or not strongly better, but noticeably better at least, was the cumulative developers over the life of the system. Okay, that's the research that we have done to this point. This is simply a list of some of kinds of things that software engineers, especially software engineers interested in testing issues, might be interested in looking at. Maybe some of you are interested in looking at some of these things, if you have access to systems that could be looked at. All of our work has been done with AT&T systems, with the exception of, the three systems in the middle that were used by AT&T but developed by a different company. And maintained by a different company. So in some sense, there's some kind of very general, there's some relationship at least among all those systems. What if we go to completely outside systems, look at stuff developed by different companies? What about open source systems? Do any of these ideas make sense for open source software? Maybe a very different, it's certainly a very different development environment. You have many people working on the code coming from sort of all sorts of places. So we asked these obvious questions, right? What are the most accurate models? That's always the question. That's the basic question that we're trying to answer. This one is, it's not an analysis question so much as perhaps a management or an organization question. right? How can you really take advantage of this? I mean, the obvious thing is it tells the developers which are the files that are most problematic and which ones you have to be most careful about. Maybe it also has some implications on how you should structure your development process. So people who are interested in managing software projects would want to consider this kind of question. It would be very useful to go below the file level. Can we make predictions not just at a file level, but can we look at individual methods within a file? Can we predict the methods that are most likely to have problems? That's a tough problem, because usually the databases that we look at that have the fault information or the change information don't go below the file level. That was certainly the case in all the systems that we looked at. If there is a bug database that tells you to the level of an individual method or some individual chunk of program, then potentially the prediction methods could be applied at that level. And that would be just that much more useful to testers and to developers. This is something we haven't looked at all, but if there are some good ways of thinking about it, would be potentially very helpful. Can we use runtime attributes? So all we've done is look at static attributes of the code. And in some sense, well, I guess you could call it static attributes of the database, right? Information that's there. Possibly some runtime attributes can help. Could be useful. And then finally, well, we've looked at essentially one way of evaluating the quality of the predictions, which is to measure the actual number of faults that are captured in the top 20% or top 10% or averaged over all those percents. Is there some other way that's more meaningful to measure the result of the predictions, or to measure the quality of the predictions? So something that one could think about. Okay, these are research questions. There also are engineering questions. If you have prediction models and you want to put these into place, you want to make them actually useful. Okay, so this is where the collaboration with industry, I think, becomes especially important, because if you don't have these things in a meaningful, useful way, industry isn't interested at all. So, okay, the first one is just extending beyond the AT&T systems that we looked at. Second is, user interface is very important. The tool that Elaine showed the pictures of, it's basically let's call it a quick and dirty prototype that was built so that we could show it to some of the AT&T development teams that were potentially interested in the tool. It's actually built. It's built in Python. It's very simple. It didn't take a long time to do, and it uses really sort of outmoded technology, very frankly. These days, you would want to have a web-based system, not a GUI interface like that. So that's important, because users want to see something that they can easily use and not have to go through big learning curves to use. And then, okay, how do you actually integrate that into a development and testing environment? And that's going to differ depending on what that environment looks like from company to company. So these are sort of more, let's say, more practical implementation issues, but they also have to be considered. Okay, so the last thing I'm going to talk about, this is, well, incomplete work, let's say, okay? Something that we started looking at, and we tried to think, if we know something about the individuals who worked on code, does that help us make predictions? So this is the Sam versus John question, right? If you know that this guy wrote the code or that guy wrote the code, can something about their previous history in producing bugs or their likelihood of producing bugs, whatever, is there some way that can influence the prediction? Can you get better predictions in this way? So we thought of two possible ways of capturing this. And first one is, so you have a release, and you know that a developer D modified some of those files in the release N. You want to know what is the likelihood of those files having bugs in the next release. And if even better, how many bugs are in that file in the next release. Okay, so first we have the buggy file ratio. He works on so many files, and in release N, and B of them have bugs in the next release, then the ratio is simply that's the percentage of the files that have bugs. So can we predict that? So we looked at this for, I guess, for just one system. So this is a real system, AT&T system. It's at least at the time point when we looked at it, had 107 different programmers working on it. And we looked at them over 15 releases. The buggy file ratio, of course, is always between 0 and 1. It's just the percentage of the files that they had. And it turns out that about 40% of the files have bugs in the next release, of the files that are worked on by all the programmers, okay? Now, realize that what does this mean, okay? If there are 1,000 files, most of them are not changed from one release to the next, okay? And most of the bugs show up in the changed files. So the 40% here, it's not 40% of all the files in the release, it's just the 40% of the changed files, okay? Which might be 20% of all the files, right, right. This might be 8% of all the files, or even fewer, okay, okay. Okay, so, as I said, the average was about 0.4, and this shows across the releases, from release 2 up to release 16, what's this buggy file ratio of all the programmers at each release. So it sort of jumps around this 0.4. Something bad happened, obviously, in this release, right? Okay, so that's everybody. What about particular people? So this is going to show two charts of two different programmers. So the guy named Y, actually I think this is a woman, right? So this is the gal named Y, did pretty well, right? The buggy file ratio for this programmer drops way down here. The numbers here are the number of files that were actually worked on by that programmer in the previous release. So here is at release 3, is it 28? Anyway, it's 28 or 25, I can't tell. The programmer worked on or changed, let's say, 28 files, and about a little more than, maybe it's 0.25. So a quarter of those files had bugs. By this time, worked on 3 files in the previous release. It looks like none of them had a bug, and generally these are pretty low. So this sounds like a programmer this looks like a programmer you're very happy to have on your project, right? Changes lots of files, and very few bugs. Very few of those files have bugs. And now this is, who is this? Maria, okay? And the next one is going to be maybe Jose, okay? And so this guy, well, okay, you would probably want to be careful about assigning programmers for him. Okay. So he has lots of, many more bugs in his program, a much higher percentage of buggy files. Okay. So as I said, there are 107 programmers on this project. If we could put all of those 107 into this class or that class, then that's really useful for the manager to know about that. It's not the case, though, right? I mean, these are the extreme cases. So this is a more typical situation, okay? So here are 2 other developers, and they pretty much follow the average of all the 107. And in fact, most of the programmers that we looked at are like this. So you don't really see this clear difference from one to the other, at least on this project, for this particular one. Yeah, wait. Okay. So this is it. This is the results, okay, of this sort of preliminary investigation into trying to capture this kind of information about programmers. And although the pictures look nice, I like the pictures, but there's lots of issues about this, and it's not clear that these are really useful things. So the first, maybe the most important thing is, just because a file that I worked on has some bugs in the next release, doesn't mean that I'm necessarily the one who put the bugs there, right? Because files are not necessarily changed by only a single developer. Files typically are changed by multiple developers, not always, but at least sometimes. So you don't know necessarily who's responsible for the bugs, at least in this way that we were measuring. Okay, there can be what are called latent faults. A fault may be introduced 5 releases ago, but it's never discovered until the current release. So the fact that I worked on that file in the previous release doesn't mean, again, and it's buggy in the next release, doesn't mean that I'm the one who put the fault there. Maybe it's already been there for 5 previous releases. Okay, this one, if you go back to this, so this looks like this programmer did very well, changed 120 files and had a very low buggy file ratio. But actually, it may just be, and in fact it turned out to be the case in many of these situations that we looked at, that these kinds of, when somebody changed this many files, they're not really doing significant changes. They're probably doing the same kind of change across many, many files in some kind of batch change. So maybe some name of some variable was changed for some reason, and they had to be changed across 100 different files. So you make one change, and so maybe 100 of these changes really should only be counted as one change. Okay. So you may change many files in an identical way. Okay, this is another one another potential problem with this, okay? Now Jose had lots of buggy files, but maybe that's because he's known to be a very good programmer, a very excellent programmer, and makes few mistakes. So the manager says, okay, I'm going to give the tough problems, the really hard problems, or the hard files to work on, to him, to be the developer, because I know he's going to be very careful. So those bugs may have been there. They may be latent bugs, or they may just be problems because it's a very difficult algorithm to implement, and it's tricky, so maybe it's more likely to have a problem there. But because he's a good programmer, he's working on those. And somebody who's not known to be a good programmer gets the easy jobs to do. Could be another reason why you get something like that. Okay, and then this just shows, okay, the bug ratios vary widely from release to release. Okay, maybe that's the case. Okay, I have one more slide, which I have to run over here to show you. Okay. So these are just some questions that you might want to think about. If you have good answers, that's great, and send me an email and let me know. Okay. So the first one is kind of basically capturing all the things that I said on the previous slide, the problems with the definitions, right? Is there really such a thing as bug proneness of an individual programmer? Intuitively, again, I guess, we probably feel like that. There are differences from one programmer to another. What's the best way to capture it? Is the information useful? A manager probably would think so. Are there better ways to measure it than the bug ratio? Maybe there are. As a project manager, you have to think about more than just the technical success of the project. You have to think about you're managing people. So how do you handle people in an appropriate way, in a successful way, and ultimately in an ethical way? So is it in fact ethical to measure this kind of performance of programmers? If you try to measure this, how do you use the information? Do you keep it private between the manager and the programmer? Do you publicize it across the project so that every programmer sees the quality of the other programmers? It's probably not a good idea, right? Yeah. So these are just some kinds of things to think about. It goes beyond the technical aspects of doing something. And if you are a program manager, a development group manager, there are things to think about beyond just the technical success of the project. So, okay, that's all. Thank you very much. I'm happy to try to answer questions if people have.
I will start just to ask you if you have used any taxonomy or defect classification or if you have those information to the criticality of the bugs and things like that. And also what would be the guidelines to feedback the development process in general. I know it depends on the process you have and so on, but what would be the main points having this experience to feedback the development process?
Okay, so the first one is easy to answer. We didn't look at any kind of category of bugs at all, essentially. In the beginning, what we did try to do was look at the rated severity of the bugs, which is something that I think pretty much all development projects do that. They have some kind of a severity classification for bugs, and from a project perspective, you always want to know the most severe bugs as soon as possible, and you want to put the most effort and the earliest effort into fixing those. So we tried to see if we could predict, or we tried to see if there was some way that it would be meaningful to address that. And the answer was we ended up no. When you look at real projects, although they do assign severities to bugs, what we found by talking to project managers is that virtually all of the bugs are classified in some kind of an intermediate rating as not super critical, but not trivial. And
something like 85% will categorize as severity 3.
Yeah, okay. Yeah.
Severity 1 is worse, which means catastrophic, you must fix it instantly. 2 is very bad. 3 is fix it. And 4 is cosmetic.
85 was
80 to 85 were in this non-critical stage. And actually, and the managers say, are proud of that. Say, look at the fact that all of our problems, virtually all of our problems are not so serious. So maybe that's true, maybe it's not true. But then talking to programmers and to testers, one starts to find out that the classifications are actually quite unreliable for a variety of reasons. And we can talk about it some more, but social reasons. So no, we did not try to do that. And in terms of more fine-grained classification, we didn't do that at all. That information, it's just not. To do that, you have to really go in and really examine each bug individually, because the databases don't have that kind of information. Okay, so that's for the categorization. Well, in terms of the feedback, how it's used. Maybe we'll go into that. But basically, the basic information is simply to tell the basic use is to tell the developers, these are the files where you have to be the most careful and where you have to to tell the testers, these are the ones that you have to test the most carefully. And to tell the developers, these are the ones where you have to be most careful, perhaps, about making additional changes. And try to be sure that your additional changes are consistent with existing code, with existing practices.
Okay. Any other question? No one?
Okay. Actually, one thing I would ask a question, which is, I could ask just you, but I could ask everybody. Is software engineering of this type of thing, which was basically based on examining large systems or doing what we call experimental studies, empirical studies, is that something that that goes on here? Are there people who are interested in this kind of work, and
yes.
is there scope for that? Is there the ability to do those kinds of things with interaction with industry?
Yes, and we have, in fact, a network in Brazil that addresses empirical software engineering, and the guy in Manaus, he's from Rio de Janeiro, Guilherme Travasso, he's going to give a talk on that. So you're going to have an overview of that. That we
Yeah.
would like to get closer to
Yeah.
those.
Okay.
So, yeah.
Okay.
No one else? Okay. Thank you.
Okay.
Tom.
Thanks.